Hello and welcome back to Dynamic System Modeling, in which we will be discuss the node method as a technique for modeling the electric systems, so we could obtain the differential equation or the mathematical model of those electric circuits. As a review, remember that if we are given an electric element or component, then the voltage across this electric component is the voltage difference across its terminals. So assume this is E1, this is E2, then E equal to E1 minus E2. The current passing through the resistor is E over R, across the capacitor CdE by dt, and across the inductor is the initial current condition plus 1 over L integral of the voltage dt. To explain the node method efficiently, I will go through an example. Assume we are given this circuit and you are asked to obtain the differential equation that governs the response or the behavior of this circuit. So we want to replace this circuit with a mathematical model. And you are given the input as the voltage source EI, and you are interested of the output voltage E0, which is across R3, C2 and L. So we are interested to look over the response of this voltage. The node method can be summarized by those three steps. The first step is that you should find different nodes. Okay, and I mean by a node as a junction that connect two different electric elements. So you have the voltage source, you have the resistor. The voltage source is made up of two terminals. The resistor is made up of two terminals. One of the terminals of the resistor is connected to the other terminal of the voltage source, and this is called the node. Okay, so the other node of the resistor is connected to another node of the other resistor, right? This is as well as given a node, and this node is as well connected to one of the terminal of the capacitor. And this is, as we can say, this is a node, okay, because it's connecting the terminal of the resistor to one of the terminal of the inductors. This is a node which connecting the terminal of the capacitor to what? To a connecting wire. But because this node and this node, between them there is only a connecting wire, which we can assume to be ideal. We can assume those two nodes to be the same. And this is the third node, okay, again, so we can assume those as one node. Similarly, those three or four nodes can be assumed the same nodes. Okay. Now, the second step, you should reference your circuit. Okay, choose one of the nodes and label it as a ground. Okay, as your reference. You can choose any node. Okay, this node, this node, this node, any node. Okay, choose one of the nodes. And my advice for you is that you should be choosing the reference near the negative terminal of the input source. Okay, so I will put this node as my ground. So the whole node is grounded, right? The third step, the final step, label those nodes. Okay, now we have this, this is a node, okay, but because it's connected to the terminal of the voltage source, which is EI, then the voltage at this node is EI, right? This node can be labeled EA. Those node, okay, or this node, okay, it is E0, right? So this is the voltage, this terminal is labeled as E0, okay? So we can say this is E0, okay? And those are the ground, okay, which is 0. Now, you should be summing the current across a certain node. Okay, so let's take this node. Okay, we have EA minus EI over R. because the current across the resistor is given by E over R, and E is the voltage across the resistor is the difference of the voltages across its terminals. So this resistor we have EA, EI, so we can say EA minus EI over R1 plus EA minus 0 E0 over R2 plus, so you covered this terminal, the second terminal, you have a third terminal which is across the capacitor, and I across the capacitor is given by CdE by dt. So C d by dt of what? EA minus the ground. So as you pay attention, what I'm doing is that I'm putting my finger at one of the nodes and start from it. EA minus EI over R1. EA minus 0 obtained by the formula of the capacitor, okay, CdE by dt, and EA minus E0. As well, we use the formula of the resistor, right? Let's do the same thing for E0. Okay, E0 minus EA over R2 plus how many wires are coming out from this node? You have this wire, 1, 2, 3, 4, right? So you should be having 4 different components or elements in this equation. So E0 minus EA over R2, E0 minus 0 governing this equation, which is IL0, okay, plus 1 over L integral the voltage E0 minus 0 dt. So E0 minus 0. The capacitance, it is CdE by dt plus C d E0 minus 0 by dt. Resistor, it is over R. E0 minus 0 over R. Okay, now let's arrange those two equations. Okay, we have EA plus C EA dot minus equal to the input EI over R1. Okay, and for this equation you could see that you have an integral and a constant term. Okay, you can eliminate them by differentiating this equation, right? So you can say E0 dot EA dot over R2, the derivative of this is equal to 0 plus 1 over L E0, right, plus C E0 derivative double, okay, plus E0 over R3 dot, right, equal to 0. Again, let's arrange it. We have minus EA dot over R2 Now let's substitute, to make things simpler, let's substitute with the numbers. We have R1 and R2 have okay, 2 ohms, so 1 over 2 plus 1 over 2 is equal to 1, so we have EA. C is 1. So 1 over L, it is 1 over half, which is equal to 2. Okay. So having those two differential equations that govern this equation, circuit, now we can see that we have EA, like we label this. This doesn't exist. It is what we did. So actually, we labeled this node as EA. So actually, this label doesn't exist. So we should eliminate this element, right? EA should be eliminated, and we should obtain a differential equation that link the input voltage to the output voltage. So what shall we do? We could use the P operator. So to eliminate EA, we could multiply by minus half B, okay. We could keep it plus, okay, because we have negative, and then we can multiply the second one by B plus 1. Okay, this element can be multiplied over this equation, this element can be multiplied by this equation, and we sum the two equations, so we could eliminate EA. Okay, so this can eliminate this. Okay, then you could have, okay, half B multiplied by minus half Okay, we could return it back to differential equation. We obtain the input-output equation, the differential equation that describes or fully describes the behavior of this electric circuit. So now we can replace this circuit with its with its mathematical model. And now we can proceed studying this model that fully describes this system. Thank you.